Here is a concept map that I have crafted as a way to represent and summarize the key concepts and the relationships to one another from this week's chapter. This concept map, which addresses the shape of distributions, begins with a look at two different graphs. One, bar graphs, and two, histograms. These two graphs are very similar in nature. In fact, they represent what are called discrete distributions. But there's one important difference. In the case of bar graphs, we're looking at representing nominal or ordinal data. In the case of histograms, we're looking at representing interval or ratio data. As for the big difference visually speaking between bar graphs and histograms, bar graphs are not continuous. In other words, you will see gaps in between each of the bars. In the case of histograms, the bar graphs are continuous, and so there will be no gaps between the bars. Taken together, we can see that bar graphs and histograms reflect and represent what are referred to as frequency distributions. But these are not the only kinds of graphs that represent frequency distributions. We can have what are referred to as curvilinear functions. I will presume that you've seen many examples of curvilinear functions, especially from your high school math class. These are the kinds of graphs that, generally speaking, represent smooth functions, and they are continuous in nature. As I'm hoping you will recall, visually speaking, your curvilinear functions have to have three components to them. There must be an x-axis, there must be a y-axis, and of course, there has to be the curve. The x-axis is important because it reveals the range of values for the variable, and they are typically arranged from lowest to highest. In the case of the y-axis, it's important to include because it stands for the frequency of each value, again, from lowest to highest. As for the curve itself, it will typically appear to touch or almost touch the x-axis at both ends of the curve. As such, the area underneath the curve, down to the x-axis, is said to represent 100% of the cases in the frequency distribution. At this point, let's turn to the center part of our concept map and take note once again that bar graphs, histograms, and curvilinear functions all reflect and represent frequency distributions. It would also be useful to note that frequency distributions need not just be represented visually, but may be represented as a table. Either way, a frequency distribution allows us to show the number of times a particular value appears in a dataset. Visually speaking, for our purposes here, we can characterize our frequency distributions as falling into two different categories, those that are symmetrical and unimodal, and those that are not symmetrical. As for those that are not symmetrical, we'll primarily be interested in those kinds of distributions that reflect a concentration of data at one end of the distribution. And there's a special name that we have to describe these kinds of distributions. These are skewed distributions, and they can be skewed either to the left or to the right of the distributions. In the case of a distribution which is skewed to the left, we can also describe it or refer to it as being negatively skewed. That is, there is a tail to the distribution which points to the left, and it shows few extremely low values. Naturally, the same sorts of things can be said of a right-skewed frequency distribution, except in this case they're referred to as positively skewed, and there are a few extremely high values, and if we were to look at the tail in the distribution, it points to the right. In this particular case, with right-skewed frequency distributions, an example that might come to mind is the distribution of wealth within a particular society. So that takes us through the entire cluster of concepts that are associated with non-symmetrical frequency distributions. And we can now turn our attention to those that are symmetrical and unimodal. The nice thing about symmetrical and unimodal distributions is that we can compare them with one another, and we do so based on the mean of the distribution and the standard deviation. In your mind's eye, if you're able to imagine two symmetrical and unimodal distributions with the same mean, you would probably see one graph which is more narrow than the other. Of course, in your mind, if the two distributions you have in mind, which are symmetrical and unimodal, do not have the same mean, then they may or may not be the same graph. Of course, this depends upon the standard deviation for both of the distributions. If they are equal, then yes, by all means, they have the same shape. But if they have two different standard deviations, then we can say that their shapes are different. You might be able to imagine a number of different kinds of frequency distributions that are symmetrical and unimodal, but let me suggest that a canonical example would be the distribution of people's heights. This brings us to the last section of our concept map, namely, those curves that we might call the normal curve. Frequency distributions that are symmetrical and unimodal, or otherwise described as the normal curve, can be defined by two things, the mean and the standard deviation. And mathematically speaking, or algebraically speaking, these curves can be represented by a mathematical formula, but I'm not going to suggest that you attempt to memorize it or even get to know it, at least not for our purposes. Further, normal curves have a mean, a mode, and a median that are all equal to one another. The normal curve also has 2 points that are referred to as points of inflection. This is a slightly more technical term, but simply refers to a change in the concavity of the curve. If you take a look at an example of a normal curve, you'll see that on both sides of the curve, because it's symmetrical, that there's a point at which the curve appears to change, where the curve appears to curve downwards, to where the curve appears to curve upwards. Both of these points are said to be one standard deviation on both sides of the mean. And if we look at the area underneath the curve between these two standard deviations from the mean, we have an area underneath the curve which is approximately 68% of the total area underneath the curve. Now, if we were to go out 2 standard deviations on either side of the mean, we would find that the total area underneath the curve between those 2 standard deviation points represents 95% of the area underneath the curve. And similarly, if we were to go out 3 standard deviations, we would find that 99% of the area underneath the curve is found between 3 standard deviations. We needn't stop there, but for our purposes that will do. Last but not least, in a normal curve, 50% of the values occur above the mean, and 50% of the values occur below the mean. And with that, this completes our full concept map for the shape of distributions.